All right, so for this I want to do another exploration, kind of like what we did with Rolle's theorem. But notice in this one, we're not doing 2 points that have the same y value. Okay, so if we sketch this here, I have the point 1, 2, and I have the point 5, 7. 5, 7. And you can draw any function you want as long as it is differentiable and continuous, okay, connecting those 2 points, all right? So go ahead and take a moment here and draw one of your own. All right, so you guys have yours drawn. I'll draw mine. Let's make it look something like that, okay? So what we want to do this time is that we want to draw the secant line from 1, 2 to 5, 7. So I'm drawing this line right here, okay? There's the secant line from 1, 2 to 5, 7. And now here's what we want to find. We want to see, is there at least one point on your graph for which the slope of the tangent is equal to the slope of the secant. That means if the slope of the tangent equals the slope of the secant, what does that mean the tangent and the secant are? They're parallel, okay? So in my case, I can draw one. It's going to be about right here. And that's going to be parallel to the secant.
Can the secant line go through the function?
Yeah, sure. You're just connecting the 2 endpoints. And 2, you may actually find more than one point where the tangent is parallel to the secant. So go ahead and draw all of them. Yeah, I think. Yeah. Yeah, some of you are going to have a few. Like, if I had drawn... Well, here, let me undo that. If I had drawn with a different color, let's say I did this function, okay? And I had gone down like this, and then up like this, and then there, okay? I'd have a couple of secants that, or tangents that were parallel. Like that one would be parallel. This one right here would be parallel. Okay? So I've got a few of them. All right? So, did anyone not find a point where they could draw a tangent parallel to the secant?
It's impossible not to find it.
Well, yeah, it's impossible not to find one. So if you didn't, then we need to help you find it, because it's there. All right?
You just can't find it.
Or you made a groundbreaking discovery. One or the other. Either way, we should stop. Okay? Everyone found one, right?
Yeah.
Okay, so I want you to examine what you've actually discovered here. Okay? The slope of this tangent, I'm going to actually just call this value of x c. All right, kind of like we did with Rolle's theorem. The slope of that tangent line is going to be what?
Equal to the slope of the second one.
It will, okay. But let's say this is our function f of x. So that would be f prime of c, right? That's the slope of the tangent.
Correct.
Okay? So at that value of c, it equals the slope of the secant. Well, I just get the slope of the secant using my slope formula, right? 7 minus 2 over 5 minus 1. So I know at some point in there, the slope of the tangent line is 5/4. Okay? Now, this actually has an application. What we just found when we did the slope of the secant line is we found the average rate of change of the function on that interval.
The secant line.
Okay, that secant line, the slope of the secant line is the average rate of change it's the average rate of change of f on the interval from 1 to 5. Okay? Those of you, when we did the previous quiz, and you were asked to find the average velocity, it was the change in distance over the change in time, right? You just found the slope from 3 seconds to 3.1 seconds, I think it was. All right? So you take the change in distance over change in time. You are finding the average rate of change, okay? The slope of that secant line, okay? Now, the application is this. It's the mean value theorem, okay? If f is continuous on the closed interval from a to b and differentiable on the open interval from a to b, then there will exist a number c in the interval from a to b such that f prime of c equals the slope of that secant line.
Okay.
F of b minus f of a over b minus a. Okay?
Why does it look like differentiation through limits or something?
It kind of does. Well, remember where we got differentiation through limits. We were taking the limit of the slope of the secant line
Okay.
as the point got closer to the one we wanted. So, yeah, this all goes back to slope. Yeah, it all ties together. It all goes back to slope. All right? So, that's why I noted down here, the slope of the tangent line is our instantaneous rate of change at c. The slope of the secant line is the average rate of change over the whole interval. Okay? And here you can see another example. We have this value of c where we have a tangent line.
So that means that at one point the instantaneous rate of change would be the same as the average rate.
Yes, exactly.
Doesn't this work for Rolle's theorem too?
Exactly. And actually, we'll see in a minute, I'm going to connect that there. Rolle's theorem is actually a special case of the mean value theorem. It's a special case where the slope of the secant line happens to be 0. Okay? We'll see that in a minute. I want to bring this to real life though, because it makes sense if you think about it. Think about driving down the road. If you went on a trip and your average speed over the whole trip was 60 miles an hour, okay, some of that time you might have been going 55, some of that time you might have been going 70, but at some point on the trip, you had to go exactly 60.
That's true.
Okay? It's kind of like the intermediate value theorem too, if you think about it. To be an average, some values have to be below and some have to be above, unless all of them are right on the average. Okay? So if I have some below and some above, the only way to get from the ones below to the ones above, I've got to go through the average at some value. Okay? So that's kind of the connection here, and that's why this mean value theorem works. And this is something that you will end up using a number of times throughout the year here. Okay? But let's go ahead and work through an example here.
So if it wasn't differentiable?
Yeah, if it were not differentiable, on an interval, let's say we've got an interval from here to here, if we had something like this, and then a jump, okay, if I did the secant line from here to here, I might have a point where it works, but I might not as well. So I can't guarantee it. This is one of those things we can call an existence formula or an existence theorem. It just says that something exists. It doesn't necessarily tell us, it doesn't tell us what it is. It just says that there is one. Okay.
Aquilo era not continuous, né?
All right, so now we have this one here. Find all values of C in the open interval from 1 to 4 such that f prime of C equals f of 4 minus f of 1 over 4 minus 1. In other words, find the values of C that the mean value theorem guarantee. Okay? So let's start here. F of 4, if I plug a 4 in, I have 4 over 4. So 5 minus 1 is 4. If I plug in a 1 to get my f of 1, I have 4 divided by 1, which is 4. 5 minus 4 is 1. So I have 4 minus 1 over 4 minus 1, which is just 1. So at some point on this graph, my slope will equal 1. Now I've got to find where that is.
So find the derivative.
So find the derivative. F prime of C is, this is 5 minus 4x to the negative 1, so
So positive 4 divided by square root. No.
positive 4 over x squared. Good. Positive 4 over x squared. Okay. And I want where this will equal 1. So, where? Yeah, x could be positive or negative 2. But what will C equal? C will only be 2 because I have the interval from 1 to 4. Negative 2 we don't really care about here. Okay? So there we go. We have C equals 2. That's the value that was guaranteed by the mean value theorem. Okay. Yeah. Yeah, guys, here's the connection between the Rolle's theorem and mean value theorem. Mean value theorem, the mean rate of change or average rate of change is the instantaneous rate of change for some value of C. Okay? Rolle's theorem, the mean rate of change just happens to equal 0. So I know there will be somewhere where the derivative equals 0. Okay, that's the connection. It's just a special case here.